Right, so last part of section 9.2 is on graphing and polar. Okay, so we're going to use the calculator a little bit to see what these graphs look like. Okay, remember that a point and polar is written as r comma theta. Okay, so we're going to start with example 5a. Okay, it's on page 488 in your book. And I'm going to graph r equals 2. Okay, we haven't done any graphing in polar yet, so I'm going to show you how to do it. Basically, just like parametric, just change the mode to polar. And now, when you press y equals, it's going to say r equals. Okay, so if you're in a function, it's y equals. If you're in parametric, you get 2. You get an x and a y equals. If you're in polar, it's r equals. You just type in 2. R equals 2. Right, and if I do zoom, let's do zoom square. What shape do I get?
Almost a full circle.
Yeah, my y min is a little off, but yeah, basically I get a circle with a radius of 2. That's it. So you're graphing every point that has a radius of 2. Okay? There's no angle specified, so the angle can be anything. Okay? So it can be radius of 2, 5 degrees. Radius of 2, 6 degrees, 7 degrees. And if you graph every point with a radius of 2, you get a circle. Right? So that's what makes polar very easy for circles. You need a single number. If you're going to graph circles in parametric, you have a sine and a cosine. It's a little more complicated. Polar, super easy to do circles. Okay. What do you think is hard to do in polar? Lines. Okay, I'm not going to talk about it right now, but lines are much harder to do in polar. You can do them, but if you're going to do lines, you're better off with y equals mx plus b. It's much easier. Right. Now, this you can't graph on the calculator. There's no way to type in theta equals. Right? So we just have to kind of think about it a little bit. Okay, what might help us to think about it is to change it. Instead of theta equals 2 radians, let's just change it to degrees. So to change it, we would
times 180.
Thank you. Divide by pi. Just approximate. It's about 114.6 degrees. About. Okay, so there's no radius here. The radius can be anything you want, but the angle has to be 114.6. Right, so somebody give me a number for the radius.
3.
6, it's off my grid.
3.
3, okay. So 1, 2, 3, and then go 114.6. Okay, so it's a little past 90. Give me a different radius.
1.
1, and then go 114.6. Okay, give me another radius.
4.
4, 114.6. Okay, what shape am I getting?
Y.
Yeah. It's not perfect, but basically I'm getting a straight line. What other kind of numbers could I use for my radius?
2.
I could use 2. Negatives. Okay. So if I went negative 2 and then went 114.6, I'd end up right there. Okay. So in polar, lines through the origin aren't too bad, but if you said I want a line with a certain slope and a certain y-intercept, that's a little more challenging to do. Okay, so that's what it looks like when you want to graph a line through the origin, and the angle is 2 radians. Okay, radius is anything you want. Just make sure your angle's 2 radians. Any questions on that?
So how do you get to 140?
This one, I just multiplied by 180 and divide by pi. Just so in my head, I can graph 114 degrees easier than I can 2 radians. If you can visualize 2 radians in your head, changing to degrees isn't necessary. Okay. Any other questions on that one? All right. All right. So next, we're going to graph a shape we haven't seen before. Okay, kind of an interesting looking shape, and we're going to try to make a table of values to help us do it. Okay, it's a shape we really need to look at in several parts in order to get the whole picture. So I want to graph this. 3 plus 3 sine theta. Okay, and the first thing I'm going to focus on is sine theta. Okay, what I've done is I just made a graph of sine theta. And I want to look at it in 4 different parts. From 0, increasing, up to pi over 2, or 90. Decreasing from pi over 2 to pi, or 180. Continuing to decrease to its lowest point at 270, or 3 pi over 2. And then back to increasing again to get to 2 pi. Okay, so I'm going to focus on those four intervals. And then if I can figure out what's happening to sine theta, then I can figure out what's happening to triple sine theta, and then we can add 3 and figure out what's happening to the radius. Because that's the goal. I want to figure out what's really happening to my radius. Right? And of course, to get a full picture, I have to go from 0 to 2 pi. Okay? That's how you get a full picture. And that's going to be like our parameter. Okay? And I'll show you when we graph it how that works. Right, so I've got 3 columns. Okay, my angle for each interval, what's happening to the sine function on that interval, and then what's happening to the radius on that interval. All right, so what's happening to my sine function as I go from 0 to pi over 2? Sine is starting at what and ending at what on the y-axis?
0.
Starting at 0. Let's try numbers. And ending at 1. Okay, so as you go from 0 to pi over 2, for your angle, sine of that angle is going from 0 to 1. Now let's figure out what's happening to my radius. Just plug each one of these numbers in for what I just circled. Okay, so if I plug in 0, what's 3 times 0?
0.
Plus 3?
3.
Okay, so my radius is going from 3. Now fill in 1. What's 3 times 1? Plus 3? 6. So over that interval, my radius is increasing from 3 to 6. Okay, I'm not going to worry about sketching it yet, but we'll come back to that.
How would you plug in 0?
Just fill in 0 for what I circled right there, sine theta.
Would you like sine of 0? You would just do 0 altogether?
Yeah, we're not filling in for theta, we're filling in for the sine of theta.
What do we have theta there for though?
Okay.
What's that?
Where would we have theta like on the left? Like on the far left?
So this is just describing our interval from 0 to 90, 90 to 180, 180, 270, and then 270, 360. Okay, what's happening to the sine function from pi over 2 to pi?
It's decreasing.
Decreasing from what to what? Yep, 1 to 0. So now it's basically just the interval above reversed. If you fill in 1 for sine theta, we just did that. 3 times 1 is 3, plus 3 is 6. What if you fill in 0? 3. So my radius is decreasing from 6 back to 3. And you're going to see symmetry when we draw it. These two parts are symmetrical. All right, let's look at what's happening to my sine function from pi to 3 pi over 2. It's decreasing. Yep. From what to what?
0 to negative 1.
Yep. Sine is decreasing from 0 to negative 1. Now let's see how that affects the radius. What's 3 times 0?
0.
Plus 3?
3.
So my radius is going to start at 3. What's 3 times negative 1? Negative 3 plus 3? 0. So my radius is decreasing all the way to 0 here. And we're going to see some more symmetry in the last section. What's happening to my sine function from 3 pi over 2 back to 2 pi? It's increasing from what to what? -1 to 0. What's 3 times -1? -3 plus 3? 0. And then 3 times 0? 0. And then plus 3? 3. So what I'm basically doing is finding how big the radius is at the end points of these intervals. I could find the radius in the middle too. I could find it at 0.5, -0.5, but I don't need to. Okay, that's enough information to make my sketch. Okay, so now let's try to sketch it.
So what are we going to use to sketch it? The final product
Yeah,
work on?
we're going to be sketching the radius. Okay, so what does my radius start at when my angle is 0 degrees? My angle is 0. My radius is 3. How about when my angle is pi over 2? It's up at 6. Right? And you have to kind of connect that with a curved segment. Okay, it's not a straight line. Just connect it kind of like that. And notice what's happening to your radius as you go from 0 to 90. What's happening to it? It's increasing, right? It's getting longer and longer till finally it reaches its maximum radius of 6. Okay, all the way at 90. Okay. Now, what's happening when as I go from pi over 2 to pi to my radius? Decreases from what to what? Yep, 6 to 3. So I'm starting at 6. My radius is going to decrease to 3. So basically, I'm just going to mirror image this. It's pretty close. All right. Now, as I go from pi over pi to 3 pi over 2, what's happening to my radius in that section?
Goes to the right, and then stays on y.
Decreases from what to what?
3 to 0.
3 to 0. Any question on that? Right, so it's starting at 3, and it's going to decrease all the way till finally at 270 I hit 0. So basically, you get that. And then what's happening to my radius as I go from 3 pi over 2 back to 2 pi? Increasing from 0 to 3. So that's kind of the shape we get.
So it's like you start at 3, which is the first order of the brackets we get, and it goes to 6, and then 3, 0, 3.
Yeah.
It's not the crossover.
And does that kind of look like anything?
Heart.
Yeah, it's supposed to kind of look like a heart. Depending on the zoom on your calculator, it may or may not look like a heart. And the name of that graph is called a cardioid.
Because of the heart, the cardio. Yeah.
Yes. So any graph of the form a number plus or minus that same number, sine theta, or a number plus or minus the same number, cosine theta, are cardioids. Okay, so mine, I think, was 3 plus 3 sine theta. Let me just graph it and show you what it looks like on here. Sine theta. Let's make our y max. Actually, we know it goes up. How high does the y max go? 6. So I know 8's plenty. How about at 180? How far over was I?
3.
So that should be fine.
Nope.
Did I set my y max? Oh, that was x max. Sorry. Y max. 8 and let's do -4. Right. So not quite the heart shape. I think mine looks more like a heart shape, but that's basically what you get. And you can see all the points we had, the 0, 6, -3, 3. That one is stretched out a little bit more than mine was, but I tried to make it look more like a heart so you could kind of get the picture. Okay. Now if you change it to cosine, what just happened?
Well, it flipped.
Yeah, sine, cosine are a phase shift of 90 degrees.
Became Pac-Man, that's what happened.
So this thing rotated 90 degrees. What's that?
Became Pac-Man.
Pac-Man?
And then I see one fish.
Maybe. Yeah. Right? So it just rotated it. Now, if you start changing these two numbers, okay, they have to be the same to be a cardioid. But let's say we make one a 3 and make one a 5. If you make them different, it's going to loop kind of back on itself. That's no longer a cardioid, right? It's kind of in the same family, but you didn't keep the numbers the same. Okay, so to be a cardioid, it can't loop back on itself like that. Okay? And we're not really going to look at that kind of graph. I just wanted to show you what happens if you don't keep the numbers the same. And theta only has to go from 0 to 2 pi to get a complete graph. If I go more than 2 pi, I'm just going to trace over what I already have. All right, so you might have noticed if you go in your window, okay, you've got your x min, x max, y min, y max. Theta min, theta max, and theta step are just like t min, t max, and t step. What if I only go to 3.14? It's only going to show half of it. Okay, I'm only getting half the shape. Okay. Now, what if let's make that back as a cardioid. Let's go 0 to roughly 2 pi, and let's go by ones. What's going to happen now? It's what?
It won't be.
It's not really going to look like a heart. How come? Yeah, it's not sketching much detail. It's going to sketch what happens at 0, 1 radian, 2, 3, 4, 5, 6, but it can't do 7. So you're going to get these kind of segments. And it doesn't connect at the end because it's graphing 6. The next point to graph would be 7. It can't do that. All right? So keep that in mind. I'd say a good value here, 0.1 would probably be perfect. Looks nice and smooth. That's good. Good. Any questions on that? That's very, very similar to parametric. Yep. The other page?
Yeah.
Oh, you just need to, yeah. All right, next thing we're going to look at is how we can convert a polar equation to rectangular. And we pretty much just use these formulas. Okay? The ones you have for Monday. X equals r cosine theta. Y equals r sine theta. R squared equals x squared plus y squared. And theta equals inverse tangent y over x. You already have all those formulas in your notes. We're just basically going to do substitution to get rid of everything that's an r and a theta. Okay? My goal when I'm done is just to have x's and y's. Set on the left? Okay. All right, so let's start with sine theta. Does anybody see a formula up above one of those four that has sine theta in it? Yep. And if I were to solve that formula for sine theta, what would sine theta equal?
Y divided by r.
What is it?
Y divided by r.
Yeah, sine theta is y divided by r. Any question on that? So I'm going to make that substitution. Okay. In place of sine theta, I'm going to plug in y divided by r. So now at least I got rid of sine. Now I don't have any thetas, I just have r's. Now, what could I do next to get rid of this r.
Why do you have y? Why do you have an r? If you have y, shouldn't you have an x?
Nope, because there's no x in that formula. No, there's just y's and r's in that one. No. If I had cosine, then yes, I'd have an x involved. But there's no x here. No x yet. Right? Now, how could I get rid of dividing by r? And if I times it here, where else do I have to do it? The other side, where else? And the 3. Okay, the only reason I did that is because now I won't have any fractions after I do that. So what's r times r? R squared. 3 times r is 3 times r. And now these cancel out. And now I don't have any fractions. That just neatens it up a little bit. Now the last thing I have to get rid of is r squared and r. Do I have a formula for r squared?
Yep.
Yeah, what's r squared?
I squared, S squared plus Y.
R squared equals x squared plus y squared. Now, if r squared is x squared plus y squared, what would r be?
X plus y.
Remember, you can't take the square root of a sum and simplify it. You take the square root, but you can't simplify it.
It is R there.
So what would r equal?
Square root of R plus Y. R plus Y. Square root of R.
X plus one.
Yeah.
Okay, don't try to simplify it, because there's nothing you can do to simplify the square root of a sum.
Square root of x squared plus y squared.
That's it. You cannot square root the x and the y. You can't do that. So r is the square root of x squared plus y squared. Okay, it's not pretty, but that's all you can do. And now change r to what we just said r equals. Square root of x squared plus y squared. Are there any r's left in that equation? No. Are there any thetas? No. It's all x's and y's. That's all you can really do. Okay. That's what the equation of a cardioid would look like in rectangular. We probably couldn't even graph that on the calculator because you have to get y by itself. But the point was I wanted you to just practice getting rid of r's and thetas, just using those 4 formulas.
And then the first part, how did you know to divide by r?
Because when I solve this formula for sine, it's y divided by r equals sine
Okay,
theta.
yeah, take out the r out of the Okay.
You divide each side by r.
Yeah, that makes sense.
That's why it's in the bottom. Okay, so I didn't use the cosine one here. I didn't need it. If I had a cosine, I would have. Hey, any questions on that? All right. So next thing we're going to look at is how to write a polar graph in parametric. Okay, we're not going to go through too much of the proof, okay, why this is true. But I'm going to tell you, if you have a graph in polar, so you have r equals something, and you want to convert polar to parametric, well, the first thing you have to do is change your letter. Polar, we use theta. Parametric, we use what letter?
T.
T. Okay, so that's step 1. Change all your letters to t's. Step 2, after you do that, write your original function they gave you, okay, except now it's going to have a t in it instead of a theta. And then on the end of it, just put cosine t. And then for the y function in parametric, take whatever function they gave you, except now the thetas are going to be changed to t's, and just put a sine t on the end of it. So you just take the formula they gave you, put a cosine on the end of it for the x's, put a sine on the end of it for the y's, and that's how you change parametric to polar. Okay, we're going to go through one right now. Okay, so here's my equation. R equals 7 sine 2 theta. And what did I say the first step was? Change your thetas to t's. 7 sine 2t. 7 sine 2t. You put your function, that's the first thing you put in both. Okay. Now, there's something you have to tack on to the end of both of them. What do you tack on to the end of the x? You put cosine t. And what about on the end of the y? Sine t. That's it. That's all you have to do to change something from polar to parametric. Write your original function with t's. Put cosine on the end for the x. Put sine on the end for the y. I'm going to graph this in polar. Then I'll graph it in parametric and show you that they look the same. Which one do you think is simpler? Polar or parametric?
Polar.
Polar. Yeah. Polar is much simpler. So let's type in 7 sine 2 theta. Let's do zoom 6. Right. So that's the shape. I'll talk more about it in 1 second, but that's the shape you get doing it in polar. Right. Now let me type it in parametric. Let's type in 7 sine 2t. Make sure you close your parenthesis. Cosine t. And 7 sine 2t sine t. Now, if we've done this right, it should look exactly the same. Notice it's even drawing it a little slower because it is a more complicated formula. Okay? I don't know if you could tell by the speed of it, but it did draw it slower. And there's your parametric. Any questions on how those came out exactly the same? Very, very easy to change polar to parametric. A few things about, let's go back to polar, because that one's easier for me to mess around with. Let's change the 7 to a 2. If you consider each one of these things a petal, what did it do to the length of the petal? Shortened it. In fact, if you had to guess, how long would you say each petal is now?
By two units?
Each petal is 2 units long. Yep. If I graph this, how long would each petal be? 6. Yeah. Okay. So the number in front controls the length of the petal. Okay. And this particular picture is called a four-petaled rose. Okay. And the petals have a length of, just take the absolute value of the number in front. So for example, if I made that a -7, the length would still be 7 units.
Would it actually draw it?
No, it's going to do a mirror image of it, but since it's symmetrical already, you wouldn't notice a difference. Maybe it started at a different spot.
That's what.
Yeah, but the final picture is exactly the same. Now, the number inside the argument controls the number of petals. If it's even, you get double the number. So if I do a 6, how many petals would I get? 12. You can count them, but there should be 12. They should be more rounded. If I wanted to adjust that, I could do my t-step a little finer. Now, if you do odd, you get exactly the number that you type in. So that's the pattern. Even, you get double the number of petals. Odd, you get exactly the number. To make it more rounded, just make your t-step a little finer. Like, could try that. Looks a little rounder, I think. Okay. So I just want you to know what those two numbers do. First number controls the length of the petal. Second number controls how many petals. And the last graph we're going to look at is a spiral. Okay, the reason this is a spiral is because if you look at the radius, it's not equal to a number. The radius is equal to an angle, which gets bigger and bigger. And it happens that the radius is exactly the same length as the angle. So if I had a spiral and my angle was 3 units, how big would the radius be at that point? 3 units. Okay? The angle and the radius are exactly the same. And let's just try graphing it over different intervals. Okay, so just type r equals theta. Let's graph it from 0 to 2 pi. Now, the biggest my angle is going to get is 2 pi. So how big is my radius going to get? Well, what do we know about the radius and the angle in this type of spiral? They are the same. So if the biggest your angle can get is 2 pi, the biggest your radius can get is 2 pi, about 6.28 units. So if I go from -10 to 10, the spiral is going to stay on the screen. Okay, and it made 1 revolution. What's going to happen if I graph it from 0 to 4 pi? It's going to make 2 revolutions. Now, what's the biggest my radius could get this time? 4 pi. Which is about 12.56. That's going to go off my screen. Probably just off the screen on the right side. I don't think we're going to have to make anything else bigger, but let's check. My only other question is the y min. Yeah, just barely. So we got to make our y min a little smaller, little lower. Okay, and there's a spiral of 2 revolutions. Okay. Now, what if I did 0 to 8 pi? How many revolutions would I get there? 0 to 6 pi would be 3.
4.
I'd get 4.
Because it's double what you had before.
Yep. So, and I'd have to set my window as big as 8 times 3.14. I'd probably go up to 30 to get it on the screen. Right. Let's try graphing -4 pi to 0. And we'll compare it to 0 to 4 pi. Let's go. -4 pi to 0. Okay, I got to set my y min a little bit more negative. Let's try, actually my x min, sorry. What's the difference between going 0 to 4 pi and 4 pi to 0?
This one starting from the outside, not the inside.
Okay, the way it drew it, it spiraled in rather than out. And how about if you compare these 2 pictures?
Mirror.
Yeah, it's a mirror image.
It's a reflection.
It's a reflection. If you flip it, now you have the same picture. Okay, let me put it back the way it was. Okay, so just mirror images it. If you were to go -8 pi to 0, you'd just get more of this picture. You'd get 4 revolutions instead of 2. What would happen if I put my theta step at like, let's say 0.5? What's that going to do to this spiral? It's going to what? Yeah, it's going to take out some detail, so it might look a little bit more blocky. I don't know if you can tell, but it doesn't look as smooth now. And that's because you didn't make it as detailed with your T-step. I would say that's probably not a good T-step. Probably could get away with 0.2, and I think it would look pretty smooth. Yeah, looks about as good as the other one. Okay. Right. Any questions on that? All right, so for tonight, as I mentioned earlier, we're going to do the take-home. The take-home is going to cover 9.1, 9.2. It is, I believe, 12 questions. It's due at 8:30. Okay, make sure you pass it in, okay, right when class starts. Okay, if you are going to be absent tomorrow for some reason, come talk to me. And I could give you it as a take-home on a different day, but I can't give it to you Thursday night, Friday night, Saturday night, Sunday night, bring it back Monday. Okay, everyone else only has one night, so I can only give you one night.